All right, let's dive into this really surprising story about how science can sometimes get things wrong, but it's probably not for the reasons you're thinking.
So, to kick things off, we're not starting in some clean, sterile lab. Nope. We're starting with a problem where the stakes are literally life and death. Okay, so picture this. You're the person in charge of safety for a brand new jet, and you have to be absolutely certain that there are no microscopic, invisible flaws in a supercritical component. We're talking about defects that are so small you can't see them with the naked eye, but under enough stress, they can lead to catastrophic failure. Right, but here's the catch, and it's a big one. Testing for these things is insanely expensive. So you can only afford to test a tiny, tiny number of samples, maybe just 6. You're making literal life or death decisions based on a handful of measurements. And this is where it gets really scary. What if, just by pure chance, your tiny sample only shows you the good parts? You look at the data and say, hey, we're good to go, all while a potential disaster is just waiting to happen. It creates this totally false and incredibly dangerous sense of security. Okay, so keep that airplane wing in mind. Now, let's switch gears and move from engineering into the very heart of science itself. Because it turns out this exact same problem, testing with really limited data, has huge consequences there too.
There's this brilliant analogy that helps explain it. Think of a scientific experiment just like a medical diagnostic test. Its one job is to give you a straight answer to a simple question. Is there a real effect happening here? Or is what we're seeing just nothing, just random noise?
And just like any medical test, an experiment can get the diagnosis wrong. This table basically lays out the 4 possibilities. You can get it right? You can find an effect that's really there, that's a true positive. Or you can correctly say, nothing to see here, when there really isn't anything, a true negative. But, and this is the important part, you can also be wrong in 2 pretty critical ways.
So let's break down those 2 ways you can be wrong. You've got false alarms, and you've got missed detections. A type 1 error, that's your false alarm. That's when the experiment shouts, Eureka, I found something, when in reality, there's nothing there at all. Then you have the type 2 error, the false negative. This is when the experiment completely misses a real discovery that was sitting right there, right under its nose.
Okay, so now that we have those ideas, false alarms and misdetections, let's turn to the patient we're actually diagnosing here. And, well, the results are pretty shocking. So get this, why most published research findings are false. Now, this wasn't some clickbait headline from a blog. This was the actual title of a groundbreaking paper from 2005 by a scientist named John Ioannidis. And it was a mathematical argument that sent absolute shockwaves through the scientific world. It was basically hinting at this deep systemic problem. And then in the 2010s, this problem got a name, the replication crisis. Researchers started going back and trying to repeat these classic foundational studies, in fields like psychology, medicine. The whole idea was super simple. If a discovery is real, someone else should be able to follow the recipe and get the same result. But a lot of the time, they just couldn't. And this just puts it in stark visual terms. A huge project tried to redo 100 different studies from top psychology journals, and the results were, well, they were stunning. As you can see from this chart, nearly 2/3, 64% of the original findings, these things we thought we knew as fact, they just vanished when someone tried to do the experiment a second time. They simply didn't replicate. So you have to be asking, why? How is this happening? Well, one of the biggest reasons is this really counterintuitive twist in statistics. It all comes down to this thing called statistical power. You can think of it as the sensitivity of your experiment. It's the ability of your study to actually detect a real effect if there is one to be found. And just like our airplane wing problem, it's tied directly to your sample size. If you have low power, it means you're working with a small and maybe unreliable sample. Now, for decades, the main thing people worried about with these low-power studies was that they would just miss real discoveries. They'd commit a type 2 error. And it kind of makes sense, right? A small sample is like trying to see details in a blurry photo. It's just hard to spot what's really there. But, and here is the paradox, the big twist. It turns out that low power does something way more dangerous. It actively pollutes the scientific record with false alarms. It actually makes it more likely that any significant finding you do get is just a total fluke, a type 1 error. Okay, now this graph really shows the paradox in action. So the up and down axis, the vertical one, That's the probability that a significant finding is actually fake, a false positive. And the horizontal axis is basically how likely you think it is that there's a real effect to find in the first place. Now just look at that green line. That represents the weakest, lowest powered studies. And notice how for almost the entire chart, it has the highest chance of being wrong. So a weak study that gets an exciting result, it's kind of like a broken clock that's right twice a day. Yeah, it might be right by pure chance, but you really shouldn't trust it.
Okay, so this sounds pretty bad. But the good news is researchers are already on it. They're working on real solutions to fix this and make science much more robust.
First, we've got to be honest and say it's not just about low power. There are other things, sometimes called questionable research practices, that make the problem worse. You have publication bias. That's where journals only want to publish exciting, positive results. So the negative or boring ones just get stuffed in a file drawer. And then there's p-hacking, which is kind of like torturing your data until it confesses. You just keep analyzing it in different ways until something significant pops out.
And this slide shows one of the most powerful fixes for this: pre-registration. It's a brilliant idea. It's basically like calling your shot in a game of pool before you take it. Researchers have to publicly post their hypothesis, how they're going to run the study, and how they'll analyze the data before they even start. This totally removes the temptation to p-hack. And it gets journals to agree to publish the results no matter what they are, based on how good the method was, not on how exciting the result is.
So, what does all this mean for us? Well, the takeaway here is not to lose faith in science. Not at all. It's about understanding that science is a human process. And a really important part of that process is self-correction. It means that when you and I see a headline about some amazing new breakthrough based on a tiny study, we should probably take it with a grain of salt. We should have some healthy skepticism.
So I'll just leave you with this final thought. The next time you see a headline about a breakthrough study based on a really small sample, what's the first question that's going to pop into your head? Will it be, wow, that's amazing? Or will it be something more like, okay, that's interesting, but has anyone been able to replicate it?